rise to any noticeable force, and that's called the Higgs boson. So the Higgs boson is the last of these particles to be discovered, and it's also the weirdest. This one doesn't fit, one doesn't make sense. You have matter particles, you have force particles, and then you have little Higgs boson up there. Why did we need to invent the Higgs boson? The idea of the Higgs was invented in the 1960s, the early 1960s. Long before it had been discovered, so clearly there was some need to invent it. And if you want to know why the discovery of the Higgs was so important, you need to know why we invented it in the first place. And that's what's difficult to explain. And the reason why it's difficult to explain, you can blame Democritus. Because he is the one who got us started thinking about particles. And if you have a little bit of physics education, you might have faced this point where your teacher, your professor is telling you, is light or is matter or electrons particles or waves? This is some sort of dichotomy you want to resolve. And I'll bet you, 10 to 1 odds, they didn't tell you the answer. The answer is it's waves. You need to understand what is going on. You actually need to give up a little bit on the notion of particles. So rather than pointing at Fermi or Democritus, my touchstone in the intellectual tradition for dealing with the real world is the Insane Clown Posse. This is a young group of, these are two singer-songwriters in the hip-hop tradition. This is Violent J, and that's Shaggy Two Dope. These are not the names they were born with, but... and, you know, they tend to have themes in their musical stylings, mostly dealing with partying and having a good time. But a couple years ago, the Insane Clown Posse came out with a song that was controversial, because it was not about partying and having a good time. That controversy had died. That was boring. They wrote a song called Miracles that was about how awesome the world around us is and how mysterious it is. And in the course of the lyrics from Miracles, the Insane Clown Posse really managed to get scientists annoyed at them. They said the following: I see miracles all around me, stop and look, it's all astounding. Water, air, fire, and dirt, gosh darn magnets, how do they work? That's not the actual word. You can Google the word that they said. And they went on and saying, you know, gosh darn scientists, you don't know anything. So the scientists were, you know, they thought about this, because their playlist naturally came up with the Insane Clown Posse. And they were puzzled, because they were like, you know, guys, magnets, it's part of our wheelhouse there, magnets. We kind of do understand how magnets work. So what I want to do, it's true, we do actually understand magnets. There are things we don't understand. Magnets, not the first thing to choose. But I want to nevertheless give some points to our plucky duo, because even though we understand how magnets work, it is still true that they are astounding. That we sometimes forget that because we understand how things work, we forget how strange it is, the way that different things work. If you think about a magnet, what does a magnet do? A magnet sticks to your refrigerator. But lots of things stick to your refrigerator. Right? A piece of tape would stick to your refrigerator. Your phone would stick to your refrigerator. That's not surprising. What's surprising is that a piece of tape, in order to get it to stick to your refrigerator, has to touch the refrigerator. That makes sense. That's sort of plain. There has to be some part of the piece of tape that is interacting with the refrigerator to keep it stuck. But the magnet, if you pull the magnet off the refrigerator, you know, it starts pulling on the refrigerator. It starts pulling toward there before it actually touches. How does the magnet know that there's a refrigerator nearby that it needs to stick to? How does the magnet reach across space and say, yes, refrigerator, good, I'm ready for this. I got this. How do they work? That is a very respectable question. And not only Violent J and Shaggy Two Dope want to know this guy, Isaac Newton. Isaac Newton, very famous for inventing gravity. He didn't invent gravity, he's been around for a long time, but he invented the law of gravity that really works. It's not the perfect law because Einstein came up with an even better one. But Newton's version of gravity is good enough to get you to the moon, for example. And it's a very simple idea. Here is his idea with the gravity is universal. And it obeys a certain very simple mathematical relationship. Here's the Earth, here's some objects, some satellites that NASA has built flying around the Earth. And Newton says there's a gravitational pull on every object that is proportional to the mass of the object pulling it, which makes sense. But also it gets fainter and fainter the further you go away as the distance squared. It's the inverse square law. The bigger the distance, the weaker the force. And that simple idea, the force of gravity goes as 1 over the distance squared, works for apples falling from trees, works for the moon going around the Earth, it works for stars going around the Milky Way. It's incredibly effective. The problem was, from the 17th century point of view, when Newton was thinking of this, it made no sense. Newtonian gravity in Newton's day was a lot like quantum mechanics is to us today. The theory that fits the data beautifully is obviously right, but there's a part of it that doesn't really make intuitive sense to us. For Newton, that's aspect of action at a distance. So you're over here, you're this guy, you want to know what is the gravitational field pulling me, right or left or whatever, what is the force? All you do to gravity, and Newton says, all you have to do to think of the force of gravity is take every object in the entire universe, figure out how far away it is, how much mass it is, and multiply the square root. It seems strange that I need to understand every object in the universe to figure out what the gravitational force is on me right here. Why? That seems spooky. It's action at a distance. It's like something going on here around the galaxy is affecting me right here, right now. And Newton was very, very bugged by this. He said, this makes no sense. I need the mechanism for how gravity actually functions to smarter people in future generations. He knew that it was a puzzle. So the puzzle actually was resolved, and then this guy does not get nearly enough credit, by Pierre-Simon Laplace in the 18th century. He was a famous physicist and mathematician. And he's famous for telling Napoleon that he didn't need to use God to explain the positions of the planets, which might seem cheeky and very out of character for Laplace, because he was basically a social climber, but his wit got ahead of him that one time. Anyway, long before Napoleon, Laplace was puzzling about this idea of gravity. He was trying to understand the shape of the Earth, the motion of the planets. What he realized is you could take Newton's theory of gravity, the inverse square law. He didn't change the theory. He said you could rewrite the theory by imagining that there is a field filling space. So what is a field? A field is just something that fills space that takes on a value everywhere. So the temperature of the air is a field. At every point in space there's a temperature value. But temperature is obviously not fundamental. It's a property of the air. The gravitational field that Laplace is talking about, this is a thing, it's a fundamental ingredient to reality. And Laplace came up with an equation that his gravitational potential field obeyed. And he says that through this equation you can exactly reproduce all the predictions of Newtonian gravity. So now here's the Laplacian picture of how gravity works. Here's the Earth. Here's the gravitational potential field has a value at every point in space. It's low here, it's higher here. And Laplace says that the force that you feel due to gravity is just the slope of this field. If it's tilting out a lot, gravity is strong. If it's tilting just a little bit, gravity is very, very weak. prediction of Newton. Why is this better in some sense than Newton? Because to figure out the force due to gravity here, I don't need to know the universe infinitely far away. If someone told me what was going on in a sphere around that particle, if someone told me the gravitational potential in some region, that would be enough. Once you invent field theory, the laws of physics are not action at a distance, they are local. The information you need is contained nearby you. The mechanism for why gravity works is now explained. It's not instantaneous weird communication over infinite distances. It's that the Earth pushes down the field right there, and that pulls the field right there, that pulls the field right there, and that pulls the field throughout the rest of space. Everything touches everything else and communicates to its nearest neighbors, not to the whole rest of the universe. So that paradigm seemed to be extremely effective. By the 19th century, we had a picture of physics where matter, stuff, was made of particles, atoms. Atoms became sort of accepted by the modern scientific community in the 19th century. And forces, we sort of made a field. The electromagnetic field was understood in the 19th century as called the gravitational field. The 20th century was more absolutist in its meaning. The 20th century comes along and says, you know what? That particle stuff is overrated. Actually, everything is made of fields. You don't need to separately talk about matter made of particles and forces made of fields. All you need are fields. That should puzzle you a little bit. How can it be? I'm telling you, and I'm not going to back off this later. This pony right in front of me is made of fields. Little vibrating numbers at every point in space are what make up this pony. Are what make up me, what make up fields. But we feel solid, right? How can it possibly be that something as tangible and solid as ourselves can be made of vibrating filling space? The answer, of course, is quantum mechanics. Quantum mechanics is what we need. And to add quantum mechanics to fields, we need quantum field theory. This unhelpful little graphic is just to point out an interesting fact, which is that to working physicists, quantum field theory is the most important thing we know. We learned quantum field theory in graduate school. There are billions of books written about it, from quantum field theory for mathematicians to quantum field theory for dummies. And how is quantum field theory possible? But it is possible. It works. The point is that when we talk about physics to non-physicists, when we popularize it, we never mention quantum field theory. We talk about particle physics, we talk about relativity, we talk about quantum mechanics, we talk about string theory in the multiverse and the anthropic principle. But we think the quantum field theory, it's too much to bother about. And as a result, no one got it when we discovered the Higgs boson. Because to understand why the Higgs boson is important, you need quantum field theory. So let me remind you, in case your quantum mechanics has become a little rusty, what quantum mechanics is all about. The motto of quantum mechanics is that what we see when we look at the universe, what we can observe or measure, is a principle very different from what actually exists out there in the universe. In classical physics and Newtonian physics, there was a particle or a field, that's okay. The particle has a position, it has a velocity, the field has a value, it has a change in time, and if you tried hard enough and worked carefully enough, you could measure any one of those values with as good precision as you could possibly want to get. Quantum mechanics says the reality is fundamentally different than that. That there's something going on that you can never see directly. That what you see when you look at the universe is different than what the universe really is. And that bugged people when it was invented and continues to bug people today. So for example, a spinning top, it turns out in quantum mechanics, the allowed values that you can measure for the spin of the top are fixed. There's a fixed set of possible answers you can get when you ask how fast the top spins. Now the minimum possible answer turns out to be a small amount of spin. So you're not going to do this experiment. Even Fermilab is never going to do this experiment. If you took this top and said, can we rotate it as fast as possible to rotate a top, it would turn around once on its axis once every 100 million times the age of the universe. So it's very slow. But if you have an elementary particle, then this discreteness of observable amounts of spin becomes very, very important. That's why quantum mechanics first came into our notice when we started studying elementary particles. So this feature that certain observable features are quantized is where the word quantum mechanics comes from. And so quantum mechanics says this idea that there's an electron, a particle, and it has a position and has a velocity is just wrong. It's not that we can't measure the position and the velocity, it's that there is no such thing as the position and the velocity. What there is a wave function. There is a wave spread throughout space that answers the question, what is the probability that we will measure the position of the electron if that's what we choose to measure? So this is an actual mathematical model of a certain wave function for an electron in an excited state. And it's saying that you're not going to see the electron out here, but you might see it up there, you're not going to see it there, etc., etc. The wave function is what really exists. It's what the field, the equations of physics govern their evolution through time. But when you look at the electron, you don't see the wave function. You see the electron in a position. And that should bother you, and we're still trying to do better. But that's how reality works. So this is quantum mechanics. Glad we got that straightened out. You add quantum mechanics to fields, and you get quantum field theory. So fields mean that the fundamental ingredients of reality are not particles. They're things that take on values everywhere throughout space. But quantum mechanics is when you look at the fields, you don't necessarily see this nice, smooth, undulating fieldness of them. If the fields are only vibrating a little bit, when you look at them, they resolve into individual packets of energy, and it's those packets of energy that we call particles. So particles are just small vibrations in quantum fields. And part of this is actually familiar to you, the light that is coming to us from light bulbs. We know that we can talk about that as a wave, an electromagnetic wave traveling through space. We talk about the frequency of different electromagnetic waves and the wavelength. But we also know that if we look at it closely enough, that light resolves into individual particles called photons. If a friend of yours, if you're camping, it's late at night, it's dark, you have a friend who's carrying a lantern, something goes terribly wrong and your friend doesn't like you anymore, so you start walking away. You see the lantern get dimmer and dimmer until eventually you don't see it anymore. That's because our eyes are not the best photodetectors we could get. Frogs, it turns out, have better eyes, more sensitive detectors in their retinas than humans do. A frog that sees that lantern walk away would not just see it get fainter and fainter. It would get fainter and fainter until it starts flickering on and off. And as the lantern gets further and further away, it's just off for longer and longer periods, and the flickers become further and further spaced apart. What the frog is seeing is individual photons hitting its eyeball. What is really happening is an electromagnetic wave is hitting the eyeballs of the frog. But the observation turns that wave into individual packets of energy called particles. And I should say, I use the word observation, so people worry that there's something to do with like consciousness or intelligence, or you're changing reality by observing it. It doesn't need to be a conscious. It could be a frog. It could be a video camera. It could be just any macroscopic collection collection of many, many different vibrating fields interacting with a single vibrating field resolves it into these individual packet-like quanta of energy that we call particles. And this explains a lot, actually. This fieldness underlying the particles we observe explains things like how can one particle change into another one? This was a real puzzle back in the early days when they discovered radioactivity. These days we know radioactivity, but in the early days they were like this nucleus of an atom is spitting out particles. It's changing into different particles. A neutron, all by itself in empty space, decays into a proton and electron. And now we know a neutrino as well. And people are wondering, was the electron hiding in there? What is going on? It's very hard if we really made particles to explain how they can change into each other. If it's fields, suddenly it makes perfect sense to us. The W boson is a field that's vibrating. It means it's a particle, but it's unstable because it has a mass. What do you mean by the mass of a field? Mass are things that are connected with particles. The mass of a particle is just the energy it requires to push the field around. The energy that is required to get the field to vibrate. Like some pieces of string are easy to shake. Some heavy chains require more effort. A heavy chain is like a massive particle. A light little piece of string is like a low mass particle. And what happens is that the empty space before your eyes right now is full of many different kinds of elementary fields that make up the universe. Not just the electromagnetic field, gravitational field, etc. For every particle that we measure in one there's a field. There's a W boson field, there's an electron field, there's a quark field, there's a muon neutrino field, and so forth. And these fields talk to each other. They interact. They're rubbing shoulders next to each other. And one vibrating field can affect the other one. It can give its vibrations away to the other fields around it. So you have the W boson vibrating. It can transfer its energy to vibrations in the electron field and the antineutrino field. So now it makes perfect sense that particles change into each other, create each other, destroy each other, annihilate. It's just fields vibrating in different ways, transferring their energy from one field to another. So that was the quantum field theory lecture. I hope all that's perfectly clear. The homework assignments will be handed out at the end of the lecture. Why did I bother telling you about quantum field theory even though nobody does? Because quantum field theory is important for two things. Why the Higgs boson is such a big deal, and what we can do next now that we've discovered that Higgs boson. So when people talk about the Higgs boson, they talk about mass, right? You've heard this. You can't avoid this. They start talking about how the Higgs boson is what gives particles mass. And I struggled because, I was writing a book about the Higgs boson that I mentioned. I've written a book about the Higgs boson. And right now on your iPhone, you don't need to wait. You can buy that on Amazon right now. And it's difficult to explain why you need a Higgs field to give mass to particles. So I thought about why the Higgs field was invented. What were they thinking? And I realized they weren't thinking about giving mass to particles at all. They were thinking about how forces work in nature. And the way that forces work, remember Newton told us about gravity, an inverse square law. The gravitational field fades away, get further and further away. Why is that? It's a simple geometric reasoning. It's because the lines of force get diluted as you go further away. It's just like that lantern moving away from you. Its brightness also obeys an inverse square law. It gets dimmer because there are fewer lines of light rays hitting your eyeballs. Not only does gravity work this way, but electromagnetism also works this way. However, the weak force and the strong force, the nuclear forces, very dramatically do not work this way. They do not stretch you the long distances that gravity and electromagnetism do. They only stretch over very short distances. The problem that was bugging the people in the 1960s when they invented the Higgs field is why were the nuclear forces so short range? It's not an accident, it's just fact. How is the math avoided? Remember again, nature will always choose the ways that make graduate students in physics the most annoying. So it turns out that the answer, lines of force over range, is entirely different for the strong nuclear force and the weak nuclear force. For the strong nuclear force, there's something called confinement. The lines of force don't just stretch out to infinity, they interact with each other. Strong nuclear force, fittingly, is strong. So what happens is that all the lines of force get bundled together and it's like they're trapped. It's like someone put a shutter around that lantern, and if your head is inside the shutter, it looks very bright. And if it's outside, you don't see the lantern at all. If your head was inside a proton, the strong force would seem very strong. If it's outside, you don't notice the strong force at all. That's confinement. Various Nobel Prizes were given away for that. The weak nuclear force is not confined, it is absorbed. What if that lantern walking away from you at night was on a foggy night? Then as it gets a little distance away, you suddenly don't see it at all. The light coming from the lantern is absorbed by the fog. The brilliant idea from the early 1960s was the following. Maybe there's a field that we haven't thought of yet that fills all of space and absorbs the lines of force from the weak nuclear force. And that's why it's short range. The lines of force just don't get very far until they're absorbed by this foggy field that pervades all of space. So just to say the same thing in different words. This thing that we now call the Higgs field was invented by like 7 or 8 different people, but Higgs has the coolest sounding last name, so his name gets attached to it. All of the other fields that we know about in nature, if you plot the value of the field, remember that's what a field is. It's something that takes on a value everywhere. Well, it hovers around 0 in empty space. There's a particle there, it'll be vibrating, but most of the time the fields are just sitting there at 0, whether it's a electromagnetic field, gluon field, quarks, or whatever. The Higgs field is way up here. Its value in empty space is not 0. So you see that the drama of what is being suggested. These guys were saying, no, it's not the weak interactions that are puzzling. It's that you don't understand empty space. It has a field in it that has tangible effects that you can go out and measure. For example, if you poke at it, you poke this field, you make a particle. We'll call it the Higgs boson. And that's what we've been looking for the 40-some years since the idea was put forward. It was as a bonus. It was in 1967 that Steven Weinberg pointed out that if you take this idea, that they were actually thinking mostly of the strong nuclear force, but if you apply it to the weak nuclear force, Weinberg said, you get a bonus which is you can explain how particles get mass. This is a little puzzle that most people weren't even really taking very seriously, but in the theories of the day, you couldn't explain why particles like the electrons and the quarks had mass at all. That's because, I'm not going to tell you what that's because, it's a whole thing and you don't want to go there, but given the fact that the world looks different in a mirror, the fact that parity, the symmetry that you'd like to see in the world between things that we see in front of us and things that they would be observed in a mirror world, in particular weak interactions, treat reality one way and mirror reality in a different way. There's a simple argument that says that means that every single particle that a weak interaction interacts with moves at the speed of light, has to have 0 mass. Einstein told us long ago, if particles are massless, it zips along the speed of light, you can never slow it down. That would be bad if that were true. If the electron were massless, remember electrons are important, they form atoms, right? They have to go around the nucleus. So if you want to have 2 atoms come together to make chemistry, it's the electrons that are doing the work. If the electron were massless, it would not ever stick Now, if you want to know about new physics we haven't yet discovered, including, let's say, I'll give you a talk a year ago, we haven't discovered the Higgs boson yet. How do you look for new physics? How do you look for physics you don't yet know? It turns out that quantum field theory tells you how to look for things you haven't found yet. It's like an amazingly wonderful fact, because in classical mechanics, you can just imagine all sorts of different ways that weird phenomena can hide from you. But this idea that the world's made of fields and the fields vibrate and talk to each other, that tells you how to look for new fields. You shake the fields that you know aren't known, they will start the other fields vibrating. And you can basically put all the two kinds of interactions on a little clock. You have a new particle, a new field. Tell me two things. Tell me, number one, how massive it is. And mass in physics corresponds to short distances, because a mass is a vibration, and the wavelength being short means the energy is high, which means there's high mass. So there's heavy particles that are corresponding to short ranges and high energies. There are light particles that correspond to long ranges or low energies. That's one thing you have to tell me. And then tell me how that particle interacts with other particles. Is it only a little bit, or is it very strongly? You will not be surprised to learn that the things we can access, the known knowns, the things we've already discovered, are the ones that stretch over large distances and interact strongly. The things we haven't found yet are those that are either too heavy, we haven't had the energy to make them, or too weakly interacting. Those are the known unknowns in David Rumsfeld's famous formulation. The unknown unknowns would just be the idea that quantum field theory is not right, which is of course always possible. There's just no evidence for it right now. So two different strategies for looking for new physical phenomena. Go to higher energy.
可以。